In this last section, we are going to talk about efficiency. And this is how much of the energy that we put in actually goes into what we want it to do or produces useful work as opposed to just kind of waste energy as heat, which happens a lot. Recall that efficiency is defined as the ratio of energy or power output to energy or power input. So we can use power or energy in both cases. And it's always the ratio of output to input. And recall that the Greek letter eta, which kind of looks like an N, but it has a little bit of a long tail and a curl at the beginning, is often used for efficiency. So as an equation, I've got eta is equal to P out, power output, over power input, pout over pin. Or if I'm thinking in terms of energy, this is E out over E in. You can do it in terms of power or in terms of energy. Either one works. Now, if you're confused about which is the output or which is the input when you have two powers or two energies, you're never going to get more power out than you put in. So the numbers on the bottom always have to be the bigger numbers, unless you've made a mistake in your calculations of your numbers and gotten a number bigger than you actually should have. So let's look at an example. Example number 6, a 60-watt light bulb is connected to a 120-volt alternating current source. It produces 58 joules of heat and light every second. It is left on for 8 hours. Electricity costs 6 cents per kilowatt hour. Find the following. So we're told it produces both heat and light. Light is actually what we want from a light bulb, so anything that's heat is going to be wasted, is not going to be considered part of the efficiency, or it's going to be a drain on the efficiency. So we want to first find the current through the light bulb. We're looking for what is I. Since we don't have anywhere in the question resistance given, we know we're not using Ohm's law. But we do have voltage is 120 volts, and we do have power is 60 watts. So that should let us find current using our P equals IV or I equals P over V. Power is 60 and voltage 120 is going to give me a current of 0.5, let's do 50 to 2 sig figs amps. So 0.50 amps, there's my current. Part B asks me to find the resistance in the light bulb. Now I actually have two choices for finding resistance. I could actually use the power formula that I found up above, which was V squared over R or I squared times R. Either one of those would work, or I can go back to Ohm's law, which maybe is a little simpler because there's no squares involved. V equals IR. I've got the voltage, I've got the current. I should be able to solve for resistance. So I've got R equals V over I. Voltage 120, current 0.5, divide by 0.5 is going to give me 240 ohms of resistance. Then I want to find the efficiency of the light bulb. In order to find the efficiency of the light bulb, it tells me I produced 58 joules of energy out, and we need to figure out how many joules are going in. Actually, we're told it produces 58 joules of heat and light every second. So this 58 joules every second is actually equivalent to 58 watts. So that's what it's producing. That's its power output. And the power input is going to be the 60 watts. For the light bulb, they always is going to take 60 watts. So then my efficiency, my eta, is going to be power output over power input is 58 over 60, which is going to give me 96.7%. It's 0.967, so multiply by 100% if you like. I can add that step in actually. Whoops. So times 100% is going to give me 96.7%. So I guess in this case they are counting heat as part of my power output, even though it's not useful technically. All right, part D, find the energy used. Well, energy is equal to power times time. We're told it's left on for 8 hours, and we're given a power of 60 watts. This is the energy used, not the energy produced. That's why we're going to use the 60 watts, the P in, not the 58 P out. The energy used is power 60 watts times time, well, 8 hours times 3,600 seconds per hour is going to give me an output or an answer of 1728000 joules, or to 3 say figs, 1.73 times 10 to the 6 joules. And the last question asks me what is the cost of energy used? Well, here's my energy, but the cost is 6 cents per kilowatt hour. So in order to be able to use this, I need to convert this into kilowatt hours. So I could either do this again using kilowatts and hours, or I can use my conversion factor to convert from joules into kilowatt hours. Make sure you're using the unrounded answer. And my number was 3.6 times 10 to the 6 joules is 1 kilowatt hour. And then once I've got a number in kilowatt hours, I can use this 6 cents per kilowatt hour, so 1 kilowatt hour and $0.06 to get my answer. So divide by 3.6 times 10 to the 6 and times by 0.06, and this tells me the cost for 8 hours is 0.0288, which is really small. And I mean, this is fine, 2 to 3 sig figs. If we wanted to think actually dollars and cents, this is like 3 cents. It's like nothing. So there you have it. That was Joule's law with power and efficiency. Good luck on your homework.